problem as one of the examples where you can, in fact, completely and exactly generate the solution, exactly, of course, within the assumptions that we make. And that was the case of a anisotropic plate with a point load on one end and a distributed load on the other. And we said this one is a reasonably common situation relating to the stiffener termination problem, where stiffeners in plates adjacent to this one at the top here would be terminating here. So the load from each stiffener would have to find its way into the plate that is shown here. So it would end up being some kind of a very localized load. And that localized load would mean that the stresses would be relatively high in the region next to that point of action of that force. And it would be necessary to come up with the reinforcements. So we're trying to see if through this solution we can at least get a feel for the size of these reinforcements. And after deriving the governing partial differential equation, we showed that the general expression is in terms of a Fourier cosine series here, and then using the equilibrium equations we can determine the other stresses. And at this point we had satisfied all the boundary conditions. If you look at the sigma y on this edge and on this edge, you will see it's 0, and if you check on tau xy on all edges, you will see it's 0. But we had not satisfied the conditions related to sigma x, which would allow us to determine finally k0 and an. And k0, again from Fourier cosine series theory or from simple integration, is the average stress. Basically, if I integrate with respect to y from one end to the other at any x location, this integral of the cosine 2n pi y over b from y equals 0 to y equals b from one end to the other would be always 0. So the second term means that the average stress has no contribution from this second term, and therefore what's left is this constant. So the constant has to equal my average stress at any x location, the average sigma x stress. And I know my average sigma x stress as being equal to the total force divided by BH, where B is the width of the plate and H is the thickness of the plate. So that fixes K0, and with that known, we can now go through the Fourier series property of each term in the series being orthogonal to any other. And if I multiply my sigma x with this cosine 2q pi y over b, where q is an integer, then this integral will only give me non-zero contributions when n equals q. Of course, to maintain equality with the left-hand side, I still have to multiply with cosine 2q pi y over b. So I multiply by this quantity both sides and integrate from 0 to b almost arbitrarily. But we know that when you integrate, then all the integrals will be 0 except the ones that have n equals q. When you do that, you will then find that this term will only give you the area under this little square, basically, because it's sigma x at x equals 0. So you will get this, which would then, substituted in solving for an, which is here, you will get all the an terms. Basically, the summation disappears because the right-hand side will only contribute when q equals n. So for only one n value at a time do you get a contribution. That, then, we can put it back into our stresses and have the complete solution. Our first check or our first evaluation before we proceed has to do with to what extent we can reproduce at the edge, at the top edge here, this step stress. So it's 0, and then it goes to a constant value and then comes back down to 0. And this helps us to pick the number of terms, because obviously as you increase the number of terms, you will get up closer and closer to the exact solution. But as long as we get close enough to this step distribution here, or step function, then we don't need to keep adding more terms, because obviously computationally it takes time. So the different cases here start from 10, I guess, and go up to 160. And you will see that, yeah, we're getting closer and closer as the number of terms increase, but even at 160, we are not perfectly close. But arbitrarily, I will say that 80 terms is sufficient, and now it remains to check whether with 80 terms, in this case, we get good enough answers. So let's compare with finite element model, which is the easiest in these cases. As a parenthesis, the laminate we're using has 4 plies of plus or minus 45. A designation with parentheses in this course would mean a fabric ply. So this is a fabric ply. It's a single ply, not 2 plies, 1 plus and 1 minus. And by the same token, if I ever write this in parentheses, that is a single ply in the 090 degrees. So basically, plus or minus 45 means that in a single ply, the fibers, half of the fibers are going in the plus 45 and half of the fibers are going in the minus 45. That's this guy here. And this one, hang on, let's go down this way, is the same thing rotated by 90 degrees, obviously. So it's like this. So the example has only 45s, basically 4 layers of this thing on top of each other. The reason for doing that in this case is because D16 is D26, so I know is D26 is 0, so I know that my assumption that went into the problem solution is definitely valid in this case. I'm plotting my axial stress, sigma x. Remember, x is running in this direction, and I'm starting from the top. X equals 0 is here. And I'm plotting it as a function of distance, x over a. So x over a equals 0 is where the force is acting, and x over a equals 1 would be at the other end. So this is the other end of the plate. This is 0. And it goes to some value, which is the axial stress divided by the far field stress. So basically, the far field stress here is the force divided by the cross-sectional area. And at the other end, where the force is applied, then we get almost 9 times that value. So if you want to think of it as a stress concentration factor, feel free. The point is that the maximum stress is at the point of action of this concentrated force. And in this case, is about 9 times, 8.5 times the constant average stress far field away from the point of action. If you look at the results, the calculated with our methods with infinite series is extremely close or very close to the finite element with small differences in this region here. And one thing we already observe is that we get to that far field value of 1 at about half the distance away from the point of action. So at about 0.4 or so, in fact at 0.3, when we are already very close to the far field value. So whatever an effect this point stress acting, this point load has, it's really significant only within the first 30% of the distance from one edge to the other. So this is an indication of the kind of reinforcement you would need. There's no point in reinforcing from here on, which would correspond to some point in the middle of the plate and moving towards the bottom end, because the stress there is already reached the far field stress. So that's the one that you would design for anyway, and there's no point in reinforcing there. But there is definitely a reason to reinforce from 0 to about 0.3 or so, at least for this specific laminate and for this stress. Remember, there's a whole bunch of stresses. There's a sigma y and tau xy stress that we also have to double check and see what they look like. So this one is the shear stress, hopefully. Yeah, this is the shear stress, again divided by the far field stress. And it's plotted as a function of y over b. So we are going from left to right. And it's done at x over a equals 0.0075. So we are not exactly at the top edge, but very close to it. Now, why are we not exactly at x equals 0? Yeah, exactly. There's no point. We know there it's 0. So plus the exact value there is where the Gaussian integration points were in the finite element model, where we know the solution from the finite elements is exact within the finite element concept. So it would be the most accurate location closest to 0 in this case that we can then use. And you can see that the two solutions are on top of each other. Now this is telling us that whatever these shear stresses do, it happens only 0.3 away from the one end and up to 0.7 or 0.6 or so, between 0.35 and 0.6, whatever. It's only in this region that the shear stresses are significant. So as far as the y reinforcement or the reinforcement in the transfer in the along a y coordinate, we would only need to reinforce the center of the plate, which you would expect because the point load is at the center. Then you would need to reinforce the center. The question is, though, how far on either side of the center should that reinforcement go? As far as the tau xy stress is concerned, you don't need to go any further to the left of this point 0.3 here or to the right of this point 0.7 because the stress there is 0. So now we're starting to not only get a good feeling the solution is good because it matches the finite elements, but also to get a good feeling for what kind of reinforcement we will need. And then we take a case of the sigma y stress. So that's sigma y. Remember, my x is going up, my y is transverse. So sigma y is the normal stress in this direction. And again, this is plotted as a function of y over b. At the same location, x over a equals 0.0075. There's a bit of a difference between the finite element prediction and the calculated, but it's quite small. And you can easily expect if you increase the number of terms, you would get better accuracy. But you can also argue that perhaps the finite element mesh, even though we checked for convergence, perhaps that could use a bit of an improvement on the type of element used and the mesh size also. Again, the sigma y stress is very close to 0 if y over b is less than 0.2 or so, or greater than 0.8. So there's again a region in the center of the plate which would require reinforcement to cover sigma y. Now you can see also at the same time that sigma y and tau xy do not necessarily correspond to the same region in the center in which they are appreciable. One was from tau xy was from 0.3 to about 0.6 or so, 6 or 0.7, while the sigma y is over a slightly larger region. So on the one hand, we have a warm enough feeling at this point that our solution is good because it's close, if not very close, to finite element results. And on the other, we think that by looking at what regions along x or y the stresses are appreciable, we can determine the regions that would need to be reinforced. So now we open up our design space, let's say, and we try different laminates. And to run this now with the solution we have would take seconds instead of hours by the time you set up and for the finite element model. And so I'm doing only 3 different laminates just to see the different trends. This doesn't mean you would only use those, and you would need either a more rigorous way of picking your laminates or definitely some other perspective that says, okay, if for some reason we need to use this type of laminate, make sure you include it in the ones you compare. What I've done here is I've included the plus or minus 45.4, which is the one we have been checking so far to compare with finite elements, which is a very soft laminate because the fibers are in the plus or minus 45 direction, then in plane in the 0 and the 90 direction has relatively low stiffness. Then I have this plus or minus 45, 0, 90 symmetric, again 4 layers, and that one is by definition quasi-isotropic. The 0, 90 is the one that we mentioned here. So we have 2 layers of this and then repeating symmetrically. So that's the quasi-isotropic with the same stiffness in every direction. And finally, we have a 0.94, so it's the same one as the plus or minus 45.4, but rotated by 90 degrees. So that one now gives us the highest stiffness that we can get using fabric material in the X and Y direction. So this would hopefully cover a wide range of stiffnesses. If you're using fabric material, if you're using unidirectional tape, then you have a larger range of stiffnesses than you can check. We're plotting axial stress. as a function of distance from the point of action of the force. We already saw the dependence from the plus or minus 45.4, and they all have similar dependence, but the distance over which they die out to reach the far field stress, or the distance over which they eventually go to 1, because this is normalized on the y-axis, is different. In fact, the 0.94 takes much longer, and it would therefore require a longer reinforcement than both of the other two. The other two seem to take about the same distance before they reach the value of 1 or reach the far field stress. So they would need a significantly lower length of the reinforcement. If I now look at my transverse stress, that's the sigma y stress, as a function of my y distance, again, I see significant differences. Now, the plus or minus 45.4, it has the highest peak, but it's confined in the narrowest region around the center, while the other two have lower peaks and they again go further out, so they would need larger reinforcement in the y direction. Notice the one that is the narrowest is the plus or minus 45.4, which basically goes to 0 very quickly. But in the previous plot, the one, well, that goes from my point. I wanted to say something like this one is not the best one here, but okay. Plus or minus 45.4 is the shortest distance here. 0.94 is the longest. And if I go the right direction, plus or minus 45.4 is the shortest here. 0.94, which is this one, is about the longest. It's about the same as the other one. So obviously, as you are trying to evaluate the size, you would not just do one location. Location x over a here is 0.005. You would have to check at 2 or 3 locations, starting from the top here of the laminate with a low applied load, to see indeed that there is no location where the stress is wider. Typically, you would expect from intuition, and that's what you would find in results, that only really close to the load application will you have the biggest values for the needed reinforcement. So if you stay close to the x over a equals 0, that would give you the biggest sizes you would need. So unless you really want to optimize the reinforcement and make it have the widest size at x over a equals 0 at the top, and then as you move away from that edge, it becomes narrower and narrower to follow the stresses reducing, you can do that. It's just much more costly, but it's also the most efficient if you are trying to reduce weight. So we saw the sigma x, we saw the sigma y, and then there is the tau xy, the shear stress, where pretty much they all are confined in approximately the same region, which is not necessarily the same region as the sigma y. So you would have to find the worst one among the different stresses for each direction of the reinforcement, the x direction or the y direction of the reinforcement. If I'm taking all this now as a reasonable, good indication of the first sizes that I would need for reinforcement, I can summarize my conclusions that axial stresses in the 0.94 panels decay more slowly, so they would require longer doublers, while the other two faster. We just saw that. But the transverse and shear stresses in these plus or minus 45.4 and the plus or minus 45.090, the quasi-isotropic panels, are more critical in terms of the peak values. Preliminary doubler reinforcements, then the length along the x would be about 0.5 times a, that's 50% of the length of the panel would have to be reinforced for the 0.94 laminate, but only 30% of the length would have to be reinforced for the other two laminates. And the width portion would be only 0.3b. That's about 30% of the width at the center would have a reinforcement. As I mentioned when we started talking about this problem, the fact that I moved the stiffener, I terminated the stiffener, not only means that I get an axial load from the stiffener transmitted to the plate, I also get a bending moment because of the eccentricity between the neutral axis of the stiffener and the neutral axis of the skin. That bending moment is not included in this analysis, so one would have to include that or read the master's thesis that a student of mine did a couple of years ago. The other important aspect, which actually is one of the major drivers, and we will see towards the end of this quarter, is that when you transfer a load from one component to another, that happens by developing shear stresses. Typically, it's like a shear lag problem. And then in order to balance the moments locally, you will need to develop normal stresses. So at the interface between the stiffener and the skin, making sure that the load which was in the stiffener eventually finds its way in the skin means that you will need to develop out-of-plane stresses. And as we said many times in previous lectures, the resin, which is the only connection between the stiffener flange and the skin, being the weakest spot, will most likely fail or has a tendency to fail. So the final aspects of this design would actually require determination of these stresses and the tendency to create a delamination or failure of the matrix in between the stiffener and the skin. But the purpose of this exercise